Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 3rd century of the Common Era, a world in transition, a China fractured by dynastic shifts and a constant turn of political upheaval. Yet, amidst the chaos, a remarkable intellectual vitality flickered. Within the court and among the scholars, a deep curiosity about the cosmos, about the very fabric of the universe, flourished. This was an era where the practical demands of governance, the need for accurate calendars, for predicting the movements of celestial bodies to guide agriculture and maintain social order, spurred groundbreaking mathematical and scientific inquiry. The development of precise measurements and predictive models was not a mere intellectual exercise. It was a matter of survival, of ensuring the prosperity and stability of the realm. It was into this environment, this crucible of both crisis and innovation, that Zhao Shuang emerged, a name that, while perhaps less familiar to the modern Western world than some of his contemporaries in other fields, represents a pivotal figure in the history of Chinese mathematics. His contributions, though rooted in the practical needs of his time, resonate with a profound understanding of geometry, astronomy, and the interconnectedness of the natural world. Zhao Shuang's legacy is inextricably linked to the Zhoubi Suanjing, a foundational text in ancient Chinese mathematics and astronomy. This work, compiled over centuries, contained a wealth of knowledge including early methods for calculating the positions of the sun and moon, as well as practical applications of geometry. Zhao Shuang's brilliance lay, however, not simply in his appreciation of the text, but in his ability to illuminate it, to expand upon its concepts, and to translate its often cryptic passages into a clear, accessible framework. He did this through his commentary, a work of such insight and originality that it has secured his place as one of the most important mathematicians of his time. His work was driven by a desire to clarify and extend the mathematical understanding of his era. He sought to provide a more rigorous and systematic approach to solving problems, to bridge the gap between abstract principles and practical applications. His commentary on the Zhoubi Suanjing provides a window into his thought processes, revealing a mind that was both deeply analytical and profoundly creative. One of Zhao Shuang's most significant achievements was his elucidation of the Gougu theorem, a Chinese formulation of what we now know as the Pythagorean theorem. This theorem, which describes the relationship between the sides of a right-angled triangle, was crucial for a wide range of applications, from surveying land to constructing buildings. Zhao Shuang's contribution lay in his geometrical interpretation of the theorem, providing a visual proof that made the concept more readily accessible and its implications more easily understood. He didn't simply state the theorem, he demonstrated it, bringing it to life through diagrams and explanations that were both elegant and practical. The Gougu theorem, in the context of Zhao Shuang's work, was more than a geometric principle. It was a powerful tool. It enabled the precise calculation of distances, the measurement of heights, and the determination of angles. It was, in essence, a fundamental building block for a more accurate understanding of the world. The theorem allowed for the practical solution of problems that were previously difficult or impossible to address with precision. The focus of this exploration of Zhao Shuang's life and work will be to delve into the specifics of his contributions. We will explore the historical context in which he lived and worked, examining the intellectual currents that shaped his thinking. We will meticulously analyze his commentary on the Zhoubi Suanjing, paying close attention to his geometrical interpretations and his applications of the Gougu theorem. We will examine his methods for calculating the heights of celestial objects and his use of mathematical principles in astronomical contexts. The journey will begin with a deeper exploration of Zhao Shuang's commentary on the Zhoubi Suanjing. This will be followed by an examination of his geometrical interpretations and applications, and then a detailed look at his methods for calculating the heights of celestial objects and his use of the Gougu theorem in astronomical contexts. We will conclude by considering the enduring legacy of Zhao Shuang, his influence on subsequent mathematicians, and the impact of his work on the development of Chinese mathematics and astronomy. The goal is to illuminate the depth and breadth of his intellect, to appreciate the lasting value of his contributions, and to understand his place as a pioneer in the history of science. It is a story of a scholar who, in the midst of a turbulent era, illuminated the world with his mathematical brilliance. He provided lasting contributions to the field of mathematics, and his work continues to inspire and inform. His insights into geometry and astronomy were not only revolutionary for his time, they also laid the groundwork for future generations of mathematicians and scientists. Having established the historical backdrop and the foundational context of Zhao Shuang's era, we now turn to the heart of his mathematical contributions, his profound engagement with the Zhoubi Suanjing, and particularly his geometrical interpretations and applications. This ancient text, a cornerstone of early Chinese mathematics and astronomy, provided the framework upon which Zhao Shuang constructed his innovative theories. His commentary, a testament to his intellectual rigor, transformed the Zhoubi Suanjing from a collection of astronomical observations into a sophisticated system of mathematical reasoning. His genius lay in his ability to connect abstract geometrical principles with practical astronomical problems, thereby forging a powerful tool for understanding the cosmos. The primary challenge of his time was the need for accurate astronomical predictions. The Chinese calendar, intrinsically linked to the emperor's authority and the stability of the empire, demanded precision. Incorrect predictions could lead to social unrest, and thus the development of reliable methods for calculating celestial events was of paramount importance. Furthermore, the ability to accurately determine the positions and heights of celestial objects, such as the sun and stars, was critical for both calendrical calculations and astrological practices, which held significant influence in ancient Chinese society. Zhao Shuang's solution was to integrate geometry with astronomical observation. He recognized that the relationships between celestial bodies could be understood and predicted through the application of geometrical principles. This perspective, remarkably advanced for his time, allowed him to move beyond simple observational data and to develop a theoretical framework for understanding the universe. His approach was not merely descriptive, it was analytical, employing mathematical tools to model and explain the movements of celestial objects. At the core of Zhao Shuang's astronomical work was his masterful application of the Gougu theorem, the Chinese equivalent of the Pythagorean theorem. Though the theorem itself was known before his time, Zhao Shuang's contribution lay in his innovative use of it to solve practical astronomical problems. He understood that the relationships between the observer, the celestial object, and the horizon formed a right triangle, and that the Gougu theorem could therefore be used to calculate the height of celestial objects. By measuring the shadow cast by a gnomon, a vertical rod used to measure the sun's position and the angle of elevation, he could determine the height of the sun above the horizon. This enabled him to develop methods for calculating the sun's altitude at different times of the day and year, contributing to more accurate calendrical calculations. To illustrate his methods, we can examine a specific example of the calculation of the height of the sun. Zhao Shuang would erect a gnomon of a known height. Then, he would measure the length of the shadow cast by the gnomon. Using the Gougu theorem, he could then calculate the angle of elevation of the sun. The longer the shadow, the lower the sun's position in the sky. Conversely, a shorter shadow indicated a higher position. This seemingly simple process, however, required sophisticated geometrical reasoning and precise measurements. The accuracy of the calculations depended on the precision of the gnomon, the accuracy of the shadow measurements, and a deep understanding of the geometrical principles involved. Zhao Shuang's approach extended beyond simply calculating the sun's height. He applied the same principles to determine the heights of other celestial objects, such as stars. This allowed him to develop a more comprehensive understanding of the celestial sphere. The ability to accurately locate and track the positions of stars was essential for navigation, timekeeping, and the construction of accurate calendars. The significance of Zhao Shuang's work lies in its foundational nature. His methods, while rooted in the Zhoubi Suanjing represent a significant advancement in astronomical understanding. He demonstrated the power of combining geometry with observation, laying the groundwork for later astronomical advancements. His work served as a bridge between the abstract world of mathematical principles and the practical challenges of astronomical observation. This interdisciplinary approach was a hallmark of his intellectual style, and it set a precedent for future generations of Chinese mathematicians and astronomers. Furthermore, the Gougu theorem itself, as applied by Zhao Shuang, has had a lasting impact. The enduring value of this theorem is evident in its continued use in various fields, from surveying and architecture to engineering and physics. Zhao Shuang's application of the theorem in astronomical contexts highlights its versatility and its importance as a fundamental tool for understanding the world around us. The methods he developed, though adapted and refined over the centuries, continue to inform our understanding of the cosmos. The legacy of Zhao Shuang's work extends far beyond his immediate contributions. He established a methodological framework that emphasized the importance of mathematical reasoning in astronomy. His work provided a model for future scholars, encouraging them to approach astronomical problems with a combination of observation, geometrical analysis, and computational skill. His legacy underscores the essential role of mathematics in the advancement of scientific understanding. He did not simply record observations, he provided a theoretical framework that allowed for prediction and explanation. In essence, Zhao Shuang's contributions represent a pivotal moment in the history of Chinese mathematics and astronomy. His geometrical interpretations and applications, particularly his innovative use of the Gougu theorem, transformed the field. He faced the challenges of his time with remarkable insight, providing solutions that were both elegant and practical. His work, a testament to the power of human intellect, continues to resonate with scholars and scientists today. His methods, his insights, and his dedication to bridging the gap between theory and practice have solidified his place as a pioneer in the history of science. Having established the groundwork of observation and calculation, Zhao Shuang turned his attention to the practical application of geometry, particularly in the realm of surveying and land measurement. This marked a critical juncture where abstract mathematical principles found concrete expression in the world around him. At the heart of this endeavor lay the Gougu theorem, a cornerstone of Chinese mathematics, which we recognize today as the Pythagorean theorem. The challenges of this era demanded precise methods for measuring land, constructing buildings, and navigating the landscape. These needs spurred the development of sophisticated geometrical techniques. Zhao Shuang's approach to the Gougu theorem was distinctly geometrical. He did transcend the abstract. He brought forth a visual, intuitive understanding. He did so by creating a diagram, now known as the Gougu diagram or the diagram illustrating the Gougu theorem. This figure, a visual proof, served as both a demonstration of the theorem and a tool for its application. The diagram itself is a square divided into smaller squares and rectangles, meticulously arranged to illustrate the relationship between the sides of a right-angled triangle. The area of a square built on the hypotenuse is demonstrably equal to the sum of the areas of the squares built on the other two sides. The essence of Zhao Shuang's contribution lies in his elucidation of this geometrical relationship, providing a clear visual proof that was accessible and readily applicable. This contrasts with a purely algebraic approach. His focus was on the spatial relationships inherent in the problem. Consider the practical implications. Accurate land surveying necessitated precise measurements. The Gougu theorem, with its associated diagram, offered a means of calculating distances and areas, even when direct measurement was impractical. For instance, determining the width of a river or the height of a distant mountain became feasible through the application of this theorem, using angles and known distances to deduce the unknown. The Gougu diagram became a practical tool. It enabled surveyors and builders to solve real-world problems. The diagram, alongside the theorem, became a standard method for calculating right angles in construction, ensuring the stability and accuracy of buildings. The diagram, therefore, was not merely a theoretical construct. It was a functional instrument allowing for precise measurements and calculations. The theorem, explained and illustrated by Zhao Shuang, provided a crucial link between mathematical theory and practical application. To illustrate this, consider the problem of determining the height of a building. Using the Gougu theorem, a surveyor could measure the distance from the base of the building and the angle of elevation to the top. Utilizing the diagram, with its clear visual representation of the relationship between sides and angles, the surveyor could calculate the height with precision. This method was not limited to buildings. It was equally applicable to surveying fields, determining the dimensions of irregular plots, and calculating areas with accuracy. The theorem and its associated diagram offered a sophisticated yet accessible method for solving complex surveying problems. The Gougu theorem was not a new discovery in Zhao Shuang's time. It was known and used in various forms. However, his contribution lies in his clear geometrical demonstration and his emphasis on its practical applications. He did not simply reiterate existing knowledge, he refined and clarified it, making it more accessible and useful for a wider audience. He provided a visual proof that enhanced understanding, and he demonstrated how it could be applied to solve practical problems in surveying and construction. His work helped standardize the methods used in these fields, ensuring consistency and accuracy. The impact of Zhao Shuang's work extended beyond the immediate applications of surveying and construction. The Gougu theorem, as explained and applied by him, became a standard part of the mathematical curriculum in China. The diagram itself became a common educational tool, helping students to understand the theorem and its implications. This emphasis on practical application, combined with clear geometrical demonstration, solidified the theorem's place in Chinese mathematics. The legacy of Zhao Shuang's work on the Gougu theorem endures to this day. The principles he elucidated are still taught and used in surveying, architecture, and engineering. Modern surveyors, architects, and engineers continue to rely on the Pythagorean theorem, which underpins many calculations in their respective fields. From the construction of bridges and buildings to the mapping of land and the design of complex structures, the theorem remains a fundamental principle. The methods Zhao Shuang employed, the diagrams he created, and the emphasis he placed on practical applications all continue to resonate. The Gougu diagram, though ancient, provides a visually intuitive proof. It offers a tangible connection between abstract mathematical concepts and the real world. It serves as a reminder of the importance of visual aids in understanding complex mathematical relationships. The diagram is still used today in educational settings, demonstrating the enduring value of Zhao Shuang's approach. The enduring relevance of Zhao Shuang's work is evident in the continued application of the Pythagorean theorem. The theorem is not merely an abstract concept, it is a practical tool. It allows us to measure distances, calculate areas, and solve complex geometrical problems. The theorem is indispensable in various fields. The theorem is essential for navigation, allowing for the calculation of distances and positions. The theorem is fundamental to the design of computer graphics, enabling the creation of three-dimensional images. The theorem, therefore, is a cornerstone of modern technology. Zhao Shuang's work underscores the power of mathematics to solve real-world problems. His geometrical approach to the Gougu theorem, his creation of the Gougu diagram, and his emphasis on practical applications transformed the field of surveying and construction. His contributions, a testament to his ingenuity and his dedication to bridging the gap between theory and practice, continue to influence mathematicians, scientists, and engineers today. His legacy is a reminder of the importance of clear, accessible explanations and the enduring value of mathematical principles. His work illustrates the profound impact of mathematics on our understanding of the world. The celestial realm also captivated Zhao Shuang, leading him to make significant contributions to astronomical calculations. The era in which he lived presented astronomers with considerable challenges, particularly concerning the accuracy of calendars and the ability to predict astronomical events, such as solar eclipses. Existing calendar systems, while functional, often suffered from inaccuracies that accumulated over time, leading to discrepancies between the calendar and the observed positions of celestial bodies. Solar eclipses, in particular, were events of considerable cultural and political significance, and the ability to accurately predict them held both practical and symbolic value. A precise understanding of the movements of the sun, moon, and earth, and the ability to model their interactions mathematically was, therefore, highly sought after. Zhao Shuang, with his characteristic blend of mathematical rigor and practical application, addressed these challenges by developing sophisticated methods for astronomical calculations. He recognized that accurate predictions of celestial events required a deep understanding of the underlying mathematical principles governing their movements. He focused on creating mathematical models that could accurately represent the positions and movements of celestial bodies, allowing for the prediction of eclipses and the refinement of calendar systems. His approach to astronomical calculation was rooted in his geometrical understanding. He utilized the principles of the Gougu theorem, which he had so effectively elucidated in his earlier work, to develop methods for calculating the relative positions of the sun, moon, and earth. These calculations were essential for determining the precise timing and duration of solar eclipses. He also incorporated concepts from trigonometry, which allowed him to model the angular relationships between celestial objects. By combining these mathematical tools, Zhao Shuang was able to create models that provided a more accurate and reliable means of predicting eclipses than previously available. The development of these models was a significant achievement. It demonstrated his ability to apply his mathematical skills to solve practical problems. His methods, while rooted in the geometrical principles of the time, represented a significant advancement in the accuracy and reliability of astronomical predictions. The ability to predict eclipses with greater precision held considerable value. It allowed for more accurate observations of celestial events. It also helped refine calendar systems. The refinement of calendar systems was another crucial aspect of Zhao Shuang's astronomical work. The existing calendars of his time, while providing a framework for measuring time, often suffered from inaccuracies. These inaccuracies arose from the imperfect alignment of the calendar with the actual movements of the sun and moon. Zhao Shuang understood that a more accurate calendar required a more precise understanding of these celestial movements. He incorporated his astronomical calculations into the process of calendar design. His mathematical models allowed him to account for the subtle variations in the movements of the sun and moon. This, in turn, enabled him to propose adjustments to the calendar, leading to a system that was more closely aligned with the observed astronomical events. Although specific details of his calendar adjustments are scant, the very fact that he applied mathematical principles to refine calendar design is noteworthy. It underscores his commitment to using mathematics to address practical problems. It also reflects a deeper understanding of the relationship between mathematics, astronomy, and the organization of society. The calendar, after all, served as the foundation for many aspects of daily life, from agricultural practices to religious ceremonies. Its accuracy had profound implications for the functioning of society. The enduring relevance of Zhao Shuang's work in astronomical calculations lies in the early application of mathematical modeling to the study of celestial phenomena. His approach, which emphasized the use of mathematical principles to understand and predict the movements of celestial bodies, laid the groundwork for subsequent advancements in astronomy. This approach is a testament to his foresight and his understanding of the power of mathematics. He understood that mathematics provided the language and the tools needed to unlock the secrets of the cosmos. Even in the digital age, the principles that Zhao Shuang employed remain relevant. The modern modern world relies on highly sophisticated mathematical models to predict astronomical events. These models are used in a variety of applications, from satellite navigation to the design of telescopes. The need for accurate calendars persists, although the methods have evolved. The underlying goal remains the same: to align the calendar with the movements of the sun and moon. The impact of Zhao Shuang's work extends beyond the realm of astronomy. His approach to solving problems, which combine mathematical rigor with practical application, serves as an example for scientists and mathematicians. His work demonstrates the value of using mathematical principles to understand and solve real-world problems. Furthermore, his contributions highlight the importance of clear and accessible explanations of mathematical concepts. His Gougu diagram and his methods for astronomical calculation were designed to be understood and used by others. This emphasis on accessibility ensured that his ideas would be shared and built upon by subsequent generations. Zhao Shuang's legacy in astronomy is a reminder of the power of mathematics to illuminate the mysteries of the universe. His work demonstrates the ability of mathematical models to explain complex phenomena. His contributions helped lay the foundation to the scientific advancements that followed. His work underscores the enduring value of mathematical principles in our understanding of the world around us. The echoes of Zhao Shuang's intellectual endeavors resonate through the centuries, a testament to the enduring power of mathematical insight and its profound influence on the trajectory of scientific thought. His contributions, meticulously crafted within the framework of ancient Chinese scholarship, transcended the mere solving of specific problems. They established a precedent, a methodology, and a vision that would shape the landscape of mathematical and astronomical inquiry for generations. The Gougu diagram, a visual representation of the Pythagorean theorem, became more than a geometric tool. It became a symbol, a readily accessible means of understanding and applying fundamental mathematical principles. Its clarity and elegance fostered a culture of mathematical literacy, enabling a wider audience to engage with complex concepts. This emphasis on accessibility was a crucial element of Zhao Shuang's legacy. He appreciated that mathematics, to truly flourish, needed to be understood and utilized by a diverse community of learners and practitioners. This commitment to pedagogical clarity ensured that his ideas would not remain confined to the ivory towers of scholarly discourse, but would instead permeate the broader intellectual sphere. His astronomical calculations, similarly, were designed for practical application. The methods he devised for determining the positions of celestial bodies, for predicting eclipses, and for constructing celestial maps were not abstract exercises. They were tools for understanding the cosmos and for organizing the human experience within it. These methods, meticulously detailed and readily reproducible, served as a foundation for further astronomical investigations. They empowered subsequent generations of astronomers to refine their models, to improve their observational techniques, and to deepen their understanding of the universe's intricate workings. The impact of Zhao Shuang's work extends beyond specific formulas and techniques. His approach to problem solving, which skillfully integrated mathematical rigor with practical application, provided a model for scientists and mathematicians alike. He demonstrated the value of using mathematical principles to eliminate real-world problems, illustrating the power of abstraction to reveal the underlying structures of reality. This approach, valuing both theoretical elegance and practical utility, became the hallmark of Chinese scientific thought. It fostered a unique blend of intellectual curiosity and pragmatic ingenuity that would contribute significantly to advancements in various fields. Furthermore, Zhao Shuang's contributions reflect the importance of establishing clear and accessible explanations of mathematical concepts. His work, meticulously documented and thoughtfully presented, served as a guide for other scholars. By prioritizing clarity of expression, he ensured that his ideas were not only understood during his time, but also preserved and built upon by those who followed. This commitment to communication, a crucial element of the scientific process, facilitated the seamless transmission of knowledge across generations. The influence of Zhao Shuang's work on subsequent Chinese mathematicians and astronomers is undeniable. His methods for calculating areas and volumes, for instance, were further developed and refined by later scholars. His astronomical models, though initially limited by the observational tools of his era, provided a framework for more sophisticated cosmological theories. These achievements, built upon the foundation laid by Zhao Shuang, demonstrate the power of intellectual inheritance. They highlight the importance of building upon the work of predecessors, of refining existing models, and of pushing the boundaries of knowledge. The enduring relevance of Zhao Shuang's contributions lies in their demonstration of the universal applicability of mathematical principles. His work illustrates that mathematics, far from being a purely theoretical discipline, can be a powerful tool for understanding and interacting with the world around us. His methods for calculating areas, volumes, and astronomical phenomena are still relevant today, not merely as historical curiosities, but as examples of the power of mathematical reasoning. The core concepts he explored continue to form a foundation for mathematical understanding. Beyond their specific mathematical and astronomical contributions, Zhao Shuang's works provide a valuable lesson in the history of science. They remind us that scientific progress is a cumulative process, built upon the contributions of many individuals across time and cultures. They show that innovation often arises from a synthesis of different perspectives, of integrating theoretical insights with practical applications. His legacy is a reminder that scientific advancement requires both intellectual rigor and a commitment to communication. The legacy of Zhao Shuang offers a compelling perspective on the history of science. His work underscores the enduring value of mathematical principles in our understanding of the world. His achievements are a testament to the power of human curiosity, ingenuity, and the capacity to build upon the knowledge of those who came before. His influence, though rooted in ancient China, continues to resonate in the broader context of scientific progress. Through his meticulous calculations, his insightful diagrams, and his commitment to clarity, Zhao Shuang left an indelible mark on the history of science. He provided a unique perspective on the intersection of mathematics, astronomy, and the human endeavor to understand the universe. His legacy invites us to appreciate the enduring power of intellectual inquiry and the profound impact that a single individual can have on the course of scientific history.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.